In the previous lectures, we have discussed how to find out the forces, moments acting on the various components of a machine when it runs. Once these forces, moments which are acting on the various components are known, we can design the dimensions or we can find out the dimensions of the various elements. So, thus we can have a physical system with basic dimensions determined by the kinematic analysis, and the actual dimensions of the components and its various elements are determined through the determination of the forces and moments. Next question is, once a machine is designed this way and fabricated, is it satisfactory or will it run properly or its function will be satisfactory? That is the question now. Now, we will now see that it is not enough to design a machine just on the basis of its kinematic functionality and the determination of the forces and moments to find out the sections and dimensions of the components. What we need for a machine to be perfect in its design and construction is that it should run smoothly. What is meant by running smoothly? So, if we have a machine just indicated by the outline and it is supported then in static condition, when the machine is not running, the support will be subjected to only the gravitational pull, which does not change with time. That means, it is a static force, its magnitude and dimension both are constant and they do not change in time. But if the machine starts running and then the support starts getting force and moment which are changing with time or varying or fluctuating with time, then the whole system will definitely have a disturbed situation. That means, it will vibrate. We all know from our experience that having a machine and if it runs and if it is not properly designed, it will vibrate. So, therefore, the condition or proper design should ensure that when the machine runs, the support which carries the whole system, that support is not subjected to dynamic forces or moments. That means, what in common terms we call that this system should be balanced. Before we take up the problem of finding out how to balance a system or when a system is balanced, let us first find out that why dynamic forces appear or they get exerted on the support once the machine starts running. Let us consider one of the component of the machine, say I, whose velocity of the center of mass is v g I, g being the point and it also has an angular velocity omega I at this instant. Let the inertial properties of this member be denoted by m I that is mass of the object, and I is the centroidal moment of inertia of the object. Then the angular and linear momenta will be given by So, when we consider all the bodies together consisting the or constituting the whole system or machine, then the total linear momentum of the whole machine will be given by the sum total of all the individual linear momenta summed over all the components if there are n number of and similarly the total angular momentum of the system will be vector summation of the individual angular momenta Now, if this momenta both linear and angular momenta remains constant with time, then external force applied by the support and external moment by the support on the body will be 0. On the other hand, if they are not 0, then what it is, let us see. Then what will happen, that if this total linear momentum changes with time, then this linear momentum rate of change is nothing but the instantaneous linear force acting on the whole system. Now, a force besides the weight can act on the system is only through the support. So, this force is responsible for this rate of change of linear momentum. So, this is nothing but m is constant. So, dVGI dt will be AGI. Similarly, the total angular momentum's instantaneous rate of change is nothing but the moment which is acting on the body from outside where alpha I is the angular acceleration of the ith component, AGI is the linear acceleration of the center of mass of the ith component. So, therefore, we find that the system or the support will receive a force from the machine like this. So, if this is the support, support will receive equal and opposite forces as an effect of the machine's running. So, what is the unbalanced force received by the support? Is nothing but minus mi AGI, which is nothing but the sum of the inertia forces of all components. So, inertia force of the ith member, if you sum it over all the members I from 1 to n, that inertia force when you sum over or the whole machine, then actually this you can say here you can give. Then you will get the total unbalanced force which will be experienced by the support. Similarly, unbalanced moment on the support will be nothing but which is nothing but the sum of inertia moment. Thus, the reason for support experiencing unbalanced force and moment is the non-zero inertia force of the system at an instant or non-zero inertia moment of each member at any instant. The only way we can have total force acting on the support to be 0 is that the total system's inertia forces all neutralize amongst themselves, or we add some extra bodies to neutralize that, and at the same time if all the inertia moments of the various components neutralize themselves, or we add something extra to neutralize the resultant, then only the total dynamic force and moment on the support will be 0 and the running of the system will be smooth and it will function properly. There will be no vibration, life of the whole system will be long. So, now therefore, we will now have to be further active in designing the machine, not just satisfying the dimensional or not being enough to produce the required motions kinematically. It is not enough for the components to have enough strength to sustain the forces and moments, but the mass distribution of the whole machine should be such that the support is not subjected to any dynamic force. Now, this apart from these forces, there is of course one static force all the time acting, that I have not shown, but it will be always there. We should remember that, that is the weight of the whole thing. But this weight is a static force, it neither changes in direction nor in magnitude, and therefore, we are not worried about that. But both this F and M will change continuously as this quantity AGI and alpha I, they fluctuate with time, because the machine members run. So, as I mentioned just now, there are two ways we can have no inertia force acting on the, or no resultant inertia unbalanced force acting on the support, is that where the individual inertia forces are balanced or rather 0, or they balance or they neutralize each other when there are more than one systems, same with inertia moments. And therefore, there are what we will now consider is that an activity to make machines run smoothly, and the whole process is called balancing. Now, in any machine we will generally have three kinds of members. Say if we take this one, so a large number of machines you will find, just I am taking an example, large number of machines consist of a mechanism what we call as slider crank mechanism. Now, here we find there are three moving objects. One, say which we call the crank, already you know, is a purely rotating member. it makes pure rotation about this hinge. Similarly, this one makes pure translation. So, this block also executes a motion which is also a simple type that we call pure translation. But the problematic component is this, which is having both a translation and a rotation. So, it is a combined motion, this we call floating members. And it is a combined translation and rotation. So, a machine in general or a mechanical system in general will consist of 3 different kinds of objects. One type where the components are executing pure rotation. In another situation, the components execute pure translation, either rectilinear or curvilinear translation. Another kind where the objects are having combined rotation and translation. So, we will take up the subject of balancing for 3 different situations. So, one is rotating body or rotary balancing. And balancing of translating object or reciprocating objects. And finally, mechanism balancing. So, in a nutshell, what we have done so far is that we have found it is not enough a machine to be designed only on the basis of its kinematic requirement and the forces and moments acting on it and strength design or rigidity design. For proper functioning of a machine, it must run smoothly, and what is meant by running smoothly is that the support on which the machine is placed are not subjected to, the support is not subjected to any force or moment that fluctuate with time. That means, it should not be subjected to any dynamic force or moment, there will be no vibration and it will run smoothly. Now, what are these forces experienced by the support? Dynamic forces. This apart from the static force weight, the dynamic force and the dynamic moment which are being experienced by the support are nothing but the sum total of the inertia forces of each of the all the components and sum total of inertia moments of all the components. We have also seen that a system or a machine will have number of components. Some of them can be of purely rotary type. An example of that is the crank of a slider crank mechanism. Some of them can be reciprocating body or translating objects as the slider of a slider crank mechanism, or it can be a floating or complex motion or combined motion body as in case of the coupler of a slider crank mechanism. And we will now handle the problem of balancing a machine, that means doing something so that it runs smoothly, all the forces acting either neutralize among themselves or we put some extra object to neutralize the resultant unbalanced forces and moments, and that we will take up one by one. First, we will take up only rotating objects and how to balance those. Then we will go for reciprocating bodies and their balancing. Finally, we will discuss something about the mechanism balancing. These balancing problems which we will take up now one by one is a theoretical way of doing it at the design stage. Sometimes what happens that after the machine is built, if it is very big and if it is placed on its bearings or on its supports, the deformations etcetera due to its gravitational pull can make the system distorted from its original idealistic design, and it may give rise to some unbalanced effects. And in such cases, it has been found that it may be necessary to do some balancing in its actual working position. That kind of an activity is called field balancing, and we will take up how to do it, the procedure and the theory of it also. Let us take up a simple case. When an object is mounted on a shaft which is rotating, let us see what will be the unbalanced force experienced by the bearings or the support. Now, we know that there can be two situations. The object itself may be of irregular shape, by virtue of which the center of mass is away from the axis of rotation, and let the eccentricity of the center of mass be denoted by E, and let the mass of the whole object which is rotating be m. There can be two situations, as I mentioned just now. One is that the shape itself is like that the center of mass is away from the axis of rotation. There can be another situation that it is a perfect disc, circular disc, and supposed to be a symmetric body, but even then the center of mass of that may have a small misalignment with the axis of rotation because of assembly problem, which is not by design, but by error. Now, when this shaft is rotated at an angular speed omega, then we all know that the inertia force of the object is what? The acceleration of the center of mass, which is towards the center, which is omega square into E, into mass, that is m omega square E, and this force will be, inertia force will be minus of that. So, it will be, this is the acceleration is in this direction, I should have indicated it. And minus m into acceleration, that is the inertia force, is the centrifugal force, you all know that. Now, so therefore, at any instant what will happen to the support? That means, this body will be then subjected to the two reaction forces will be acting on this, whose resultant will neutralize and in this direction. So, therefore, for dynamic equilibrium of this, the two bearings or support will be subjected to two forces whose resultant is equal and opposite to this. And since the whole thing is rotating, these two forces which is also in the same plane, that means the plane constituted by R A and R B, also contains the force, centrifugal force, and the whole plane is rotating with a speed omega. So, for these two forces, though their magnitudes are fixed, their direction is continuously changing. That means, it is a dynamic force, and as a result the bearings, if you see the bearings or the support, if this be the support, then this will be subjected to forces like this. So, the supports are also subjected to the opposite of these forces and which rotate along with this shaft. So, therefore, the support is subjected to a dynamic force. Now, this is a very complicated way of drawing all the time. So, henceforth what we will do, we will have a simplified way of representing a dynamic body, a rotating dynamic body. If this be the support axis, then let this be the eccentric mass, and now as we find that it is the product of the mass and eccentricity which determines the force besides omega, we will always represent the unbalance as a product of the mass of the object and the eccentricity of its CG from the axis of rotation. Now, the simplest way to resolve, that means, if we have to balance this, what will be the simplest way? We will say that we can add another mass here m b at an eccentricity E b, so that m b E b is equal to m e. If that happens, then the centrifugal forces of the two bodies, one originally existed of the system and another one added later. So, they will neutralize each other, and so therefore, there will be no resultant force on this support. What we have done by doing this is effectively we have brought the center of mass of the total object just on the axis of rotation. If the resultant center of mass comes on the axis of rotation, resultant inertia force will be 0, that is resultant centrifugal force will be 0. Sometimes it may happen that there is no space of adding a mass like this. So, in such cases also there is no problem. What we can do? We can add two masses instead of one. So, we will call m a b E b E a b, m b b E b b, in such a way that we call this as, or rather I will follow something which I will take up later also. I will represent this by 1 and 2. M b 1 E b 1, M b 2 E b 2. This is A 1, this distance is A 2 and this distance is A. In such case, we have to satisfy two conditions, that the resultant centrifugal force by these two balancing masses produced is equal in magnitude and of course, opposite in direction with that. So, that will tell us that since all of them are rotating at the constant angular velocity or at the same angular velocity omega. So, their total centrifugal force of the balancing masses will be equal to the centrifugal force of the unbalance if this equation is satisfied. So, this will ensure that the sum total of the two centrifugal forces here is equal to the centrifugal force of the original unbalance. So, they will neutralize, but to neutralize that we need another condition, that they must also be equal and opposite and pass through the same line. Now, the condition which will tell that the resultant of these two centrifugal forces will pass through this point, you all know from basic mechanics, is that so, this is the condition which need to be satisfied if the resultant of the two has to also pass through the same point along which the original unbalanced centrifugal force is working or acting. So, therefore, we have two equations and we have two unknowns. Now, as I have mentioned already, it is the product of the mass and the eccentricity which is dictating. We cannot individually find out mass and eccentricity unless other conditions are prescribed from design point of view. But we can definitely find out this unbalance and this unbalance satisfying these two equations. We have two unknowns MB1 EB1 and MB2 EB2. These two unknowns can be determined following these two equations. And in this case, even if they are not along the same direction, the resultant system will be free from any unbalanced forces as experienced by this support. But there is a difference which you should not forget. In this case, the force which was acting here is neutralized by the force here, both were equal. In this case, what happens? The force which was here is neutralized by two forces like this. The difference is that though so far as the supports are concerned, both will be free from dynamic forces. In this case, the shaft is completely free from any effect due to the centrifugal forces. There will be no bending moment or stress to which this shaft will be subjected to. On the other hand, here you will find this portion of the shaft will be subjected to a bending moment, and therefore, definitely it will be subjected to some stress because of the rotation. And if the rotational speed is very high, this bending moment here can be of course important for the design of the shaft. So, to finally to say that in this case the balancing is absolutely complete, even internally there is no effect to be seen, and that is called internal balancing. Or the system is internally balanced. In this case, it is not completely free from stresses etcetera due to rotation and unbalanced forces, but the support is free from that. So, we call it external balancing, or the system is externally balanced. So, there can be two different situations. In rotary balancing, there is another situation which we have to keep in mind. What we are doing, it may appear that our primary objective is to shift the center of mass to the axis of rotation. When it happens, then the resultant centrifugal force is 0, but that may not be always enough for balancing. That means, if we take a disc or a rotor and we put it on some very free bearing, if the system is completely balanced, that means the center of mass of the whole thing is exactly on the axis of rotation, then you can put the whole system at any position, it will remain there. That means, it will be in static condition, you can put it anywhere, it will appear to be balanced. Such systems are called static balancing, and for static balancing what is needed? That the center of mass has to be on the axis of rotation. That means, Now, if we have two unbalances in such a way that their center of mass is here, then this system in static condition it will appear that it is balanced, because you can put it in any angular position on a free bearing, it will remain there. So, this is a statically balanced case. So, this rotor or rotating object is statically balanced. But what happens when it starts rotating? Moment it starts rotating, these centrifugal forces will appear, and this centrifugal force and this centrifugal force, they will produce a couple, and when this is rotating, in rotating condition, these two forces, equal and opposite forces, they are going to produce some unbalanced force on this, because now this couple which is acting on this shaft will need to be neutralized by equal and opposite couple produced by the bearing reactions, which are also in that case equal and opposite. Only thing what you have to satisfy is that if this is F and this is A, and if this is L, then F into A, this couple must be balanced by the couple produced by the bearing reactions R into L. But nevertheless, we find the bearings are subjected to two forces which also rotate along with the rotor, and therefore, these are dynamic forces. So, as soon as it starts rotating, the bearing starts experiencing dynamic forces. So, therefore, the same system which appeared to be perfectly balanced in static condition becomes unbalanced in the dynamic condition. So, this system is statically balanced, but dynamically unbalanced. Now, to balance this, what we have to do, that means, if we have to produce a rotating object which is both statically and dynamically unbalanced, we have to ensure that the resultant force and resultant moment produced by the objects then what we can do, so if we add these two objects in such a way that it produce a couple, if this is B and that is A, then the couple produced by this when M1 E1 is equal to M2 E2, that is the condition for static balancing. Now, if we have MB1 EB1 which is equal to MB2 EB2 and MB1 EB1 into B is equal to M1 E1 into A. This will produce an equal and opposite couple. So, that the unbalanced couple produced by these two masses will be neutralized by the unbalanced couple produced by the other two balancing masses. So, the resultant moment and resultant force both should be 0. So, this is the condition for dynamic balancing. This is condition for static balancing or simply force balance. So, when both the conditions are satisfied, condition for force balance and condition for moment balance, then the system is dynamically balanced. Next, what we want to do? We want to show that any rotor consisting of any number of unbalanced masses can be balanced by two balancing masses at any two chosen plane. These any two chosen planes which we can take for putting the balancing masses, of course, depend on the design considerations and other features of the system. But theoretically any two planes you can select where you can put two balancing masses that can balance any rotor with any number of unbalances. It is extremely important, this theorem, because that shows that to balance any rotor, because even a continuous rotor may be treated as an infinite number of thin disks which are individually unbalanced. And so, even a continuous rotor can be balanced by only two balancing masses placed at your chosen planes. Now, let us take first two planes. Let us draw it like this. So, let this be plane A, this be plane B, and this is the shaft which carries the unbalances. So, let us consider a case with 3, as you will see very soon that irrespective of the finite number I am selecting, so let us consider only 3 unbalances here, M1 B1, M2 B2 E2 and M3 E3. Now, it means what? That this will produce a force F1 this will produce an unbalanced centrifugal force F 2 and this one will produce an unbalanced centrifugal force F 3. Now, let us consider these distances so let this be A 1, let this be A 2 and let this be A 3. The location of these unbalances and the overall distance between the two planes is a capital L say or say A. Now, any force here can be represented by two forces. That means, suppose if I have a force acting here F, I can always represent it by two forces at any 2 points by F 1 A and F 1 B. So, that these two forces resultant is F 1. So, I can replace this force by this. So, therefore, what I can do? I can replace this force F 1 by two forces, one is F 1 A, another one is F 1 B, and there is no more force here. Similarly, this force F 2 can be also split into two forces in these two planes, and this is F 2 A and this will be F 2 B. And since I have replaced this force by these two, there is no need to have this. And finally, this force can be also replaced by two forces F 3 B and F 3 A. The magnitudes can be easily figured out how it is going to be. As you can say, if this distance is A 1 and this distance is A, as I have chosen here, then we will have F 1 A plus F 1 B must be equal to F 1 and F 1 into A 1 must be equal to F 1 B into A. This is the condition, or these are the equations to be satisfied if this force system is to be equivalent to this force, single force. So, now you see what we have, the two planes, all the unbalanced forces are represented by an equivalent system in which, say, let us draw the situation now. The situation is now like this, that we have a shaft we have F 1 A F1 B F1 F2 A F2 B and F3 A and so this force system is equivalent to the 3 centrifugal forces at these 3 locations. So, what we get now finally is that the resultant force acting, that means now this is again equivalent to what we do, we can add these 3 force vectors and this becomes the resultant. So, we can say this location the resultant force is R A and the resultant here of these 3 vectors, if we add F1 B, F2 B add, then add this. So, this is R B. So, resultant here will be so finally, we have found that the 3 centrifugal forces which we had can be represented by these 2 forces at these 2 locations. Now, these 2 locations are arbitrarily chosen where depending on your convenience, that where you select the 2 planes, and once a system you have where you have 2 unbalanced forces, to balance it is very simple by putting two balancing masses MBB EB MB A EA, so that this centrifugal force and this centrifugal force they exactly neutralize each other. So, therefore, with this system of 3 unbalanced objects, if you put 2 balancing masses here, MBA EA and MBB EB, then these 5 objects will balance each other. There will be no unbalanced force or no dynamic force experienced by the supports. Now, we have shown this whole thing with 3. This number could be any, because each and every force, centrifugal force, we can replace by 2 forces in the 2 planes, and the sum total of all these forces which we have placed here can be represented by one resultant, which can be neutralized by a centrifugal force produced by a suitably placed balancing mass there. Same thing happens here. So, if we consider even a continuous rotor, which can be considered to be then this can be split into thin discs, infinite number of thin discs, and each one of these discs may have its own unbalance, but it does not matter even if the number is infinite, because it can be always balanced by only 2 balancing masses placed at 2 suitably chosen planes, which depends on the designer's convenience. So, this is a graphical description of the whole thing, but I think we can sometimes find it convenient to solve such problems in an analytical procedure, which I will start discussing in the next lecture.